I will start the recording. Great, looks like we're recording. So hi everyone, welcome to the 73rd Dapr community call. It's November 30th, 2022. I'm the host today. My name is Nick Greenfield, and I'm a Dapr maintainer of the documentation repo. So two items on our agenda today. First, I actually will take the first topic, which is a look at the new Resiliency QuickStarts. And then I will hand it over to Michael, who will talk a little bit about the Dapr SDK for WebAssembly. And then, as always, granted, if there's time, we'll leave room for an open discussion where anything that's top of mind Dapr related, we can just have a kind of discussion at that point. So with that, I'll kick things off and talk a little bit about the new Dapr Resiliency QuickStart. So this is the Dapr QuickStarts repo, and you can see here these are sorted by the building blocks, right? And now Resiliency is a new top level directory in here. But you'll notice it's a little bit different when you go into this path here, because there is no source code in this directory. What you actually have are markdown files, and that's because this QuickStart's a little bit different. We're actually leveraging existing QuickStarts to showcase some of the Dapr resiliency capabilities. And so specifically, we're showcasing resiliency in two ways. One is the service-to-service communication, and showing how if a call using the service invoke API was to fail, how you can recover with resiliency policies. And then also the service to component. So we'll leverage the state management QuickStart to show that. So if your state store was to go down, how you can recover from that and apply those policies. So you're always welcome to jump into the QuickStarts repo and kind of from the GitHub point of view, but we also have added these QuickStarts into our actual Dapr docs repo as well. So you'll notice there's a new resiliency section. If you click on this, you get your options here, right? Do you want to see resiliency with that service to component or service to service? And so if I was to click on service to component, you can actually see this example here where if I have a service that's writing state to my Redis state store and that operation was to fail, how do the resiliency policies get applied? And so you can kind of pick your language of choice based on your the flavor language that you're familiar with, and then you can walk through these this QuickStart and see that these policies that we've defined here and how they get kicked in when an operation was to fail. And so I'll actually just walk us through this one because it's really, really quick, probably less than 5 minutes to actually showcase Dapr resiliency in this QuickStart. And so what I will do is, I guess we'll first take a look at this resiliency policy that you'll now find in, it's located at this moment next to your components. But here is the policy the resiliency policy that you'll find in these QuickStarts here. And so you can see here, it's very simple, just two policies. There's a retry forever. So if any request was to fail, in this case, a request to a state store was to fail, it's going to retry that request indefinitely. And then I have one more resiliency policy that I've defined called, which is a circuit breaker called simple CB. And it actually just says, hey, if I encounter 5 or more consecutive failures in a row, actually open this circuit so those requests are kind of stopped for the moment. All right, so really simple resiliency policy that's included in this QuickStart. And so what we'll do is we'll run that one order service that's going to be persisting state to that Redis state store component that I have on my machine that we get when you Dapr init. Let's hope this just works first time. Cool. And so I have it persisting, right? State over and over, it's persisting, retrieving, deleting. And what I'm going to do actually, just to simulate a failure in these QuickStarts, is I'm just going to stop my Redis instance on my machine. So I'm just going to do Docker stop Dapr Redis. And since I started this service with that resiliency spec being loaded, you can see as soon as that component went down, my policies are being applied. And so now it's doing the retry, right? And this will just keep retrying. It will only, it's not as, we don't want to spit out retries for every retry because that would flood the logs. So it's just going to retry until it hits that 5 retries. right? And then you can see that that circuit breaker now has just got kicked in, right? And so it went from that open to half open. Going to try a request to see if it can get through. If it fails, it's going to go back to open. It's going to keep doing that circuit breaker open, half open until that request can successfully go through. And so it's going to continue doing this as long as my Dapr Redis instances or my Redis instance is no longer running. If I restart Redis, you should see it recover seamlessly, right? It picks up right where it left off. So that's it. That's this is, I think, what we wanted to focus on here is just how do we show resiliency in action in really less than 5 minutes, right? And so that's it. Okay. Any questions on that before we move on? Looking at the chat real quick. Very nice. Okay, cool. All right, with that, I'm going to hand it over to Michael, who is going to talk about our next topic for the day, which is the Dapr SDK for WebAssembly.
All right. Thank you, Nick. Yeah, that's yeah, it's a very nice demonstration. That's I love how the quick start documentation was structured. I wish WasmEdge would have better documentation. So a lot to learn from you guys. Yeah. So yeah. So shall I start? Yeah.
Yeah. Do you want to share your screen and take over? Do you have more control?
Yeah. So I should share the Google Docs as well, right? So that I can okay. So let me do that. Okay. I should make it. Okay. All right.
Looks good.
Yeah. Yeah. Sorry, this slide has the wrong logo. Because I just made changes directly on it. I was somehow I can't remove the background from the KubeCon. So please bear with us. That's yeah. So I think in 2 meetings we talk about Dapr and WebAssembly, and last week Yaron's talk I thought was very, very interesting. It's focused on how Dapr could extend the capabilities of the current WebAssembly runtimes, and so my talk would be the other side of the same coin. It's the same issue, but but attack it from another angle, is to see how WebAssembly helps Dapr, in the world of microservices. How WebAssembly can make the by incorporating WebAssembly, how it can make the whole microservices world, I would say, perhaps simpler, but definitely faster and smaller. So so that'd be the topic of this talk, and the particular project that I want to mention is the WasmEdge project. So I put the GitHub link here. We're gonna talk about that in a minute. That's we're gonna talk about the things that at WasmEdge that we have done specifically to enable microservices type of applications in WebAssembly, and how that interacts with the Dapr SDK so that it can consume Dapr services in that in that service environment. So let's just have a very quick review of how let's say a Dapr web service is done today, right? So one of the most interesting aspects of Dapr is that it's language agnostic, like WebAssembly, right? So you can write web microservices in your favorite programming language, and then you use the a Dapr API and SDK to access the services on the sidecar. Like we just saying, that's without the Dapr sidecar, you may not be able to do resilience, or it may be difficult, complicated for you to do service calls and service component calls, and using that, using the infrastructure provided by the Dapr sidecar in SDK, you were able to do that. So basically, the application users can focus on building the microservice itself. And in our world, the microservice is typically a native application written in Go or Rust, or it could be a application that runs inside a managed language runtime, like a Java application in JVM, or a JavaScript application in V8 and Node.js, and things like that. And then once the service is developed, now you can deploy it. The typical deployment option, in production at least, is to deploy the microservice in its own container, and then the Dapr sidecar in its own container. So you have two containers side by side, and they interact with each other, right? So that's that's basically what's the state of the art today, right? That's how we do things. But what not to like? I think there are a couple of things that happened, only in just the last month. The first is that people have a lot more awareness about microservices these days. One of the unfortunate event or fortunate event, that's depending on your point of view, is Elon Musk's takeover of Twitter, right? That's after that, he basically mentioned, that's he used the wrong term, that he said, he can't understand why Twitter has 1,000 RPCs. But what he really means is 1,000 microservices, right? That's I think that comes as a surprise to a lot of people, is that you have a seemingly a simple internet service. Why would you need so many microservices on the back end? And but of course, Twitter is, in fact, if anything, Twitter is not the most aggressive in pushing microservices. If you look at other big internet companies, which we will not really name names here, but essentially all of them, they would have far more than a couple thousand web services, microservices, right? So when you have that many microservices, how do you manage them? How do you make them performant? So the first issue to say that's to have all the services running inside Linux containers. The first issue you encounter really is that it's heavyweight, because it's on the back end, if you have thousands or tens of thousands of services, and each service needs multiple instances, some may only need one instance, some may need multiple instances, you quickly have tens of thousands of Linux containers running, right? That's and all of them. Although there's argument to be made that you can make Linux container really, really small by not including Linux in it, right? Just have a container. But however, to do that, you encounter the problem of the last one. Is that you reduce the portability of your runtime, which is one of the major benefits of why people use those containers, because now you don't have the the environment, the libc or the Linux API libraries that's embedded in the container. You would have to make sure your application that it can run on whatever the host that's the container is running on, right? So in general, setting up Linux container per one container per microservice or several containers per microservice is a heavyweight process. And in production, a lot of those microservices companies today has adopted, a technique, what we call bundling, right? Meaning that to combine multiple microservices in a single container. So through analysis of invocation patterns, you could figure out that those 20 or 30 microservices are typically invoked together. So you put all of them you bundle all of them in a single Linux container and keep it warm, right? And that's really it's very burdensome to the IT folks. So this is one of the issues. That's to have each microservices individually deployed is often result in a heavyweight setup. And the second issue really is related. It's a startup time for a service inside a Linux container is slow. So I'm here at I guess I'm fortunate. I'm here. I don't have snow or anything. I'm here in Las Vegas at the AWS reInvent event, right? So the opening keynote, Peter DeSantis has spent about half an hour talk about how to improve startup time, code startup time in Lambda, and because that's obviously it has become a problem, right? That's if you search that's people's complaints or people's issues about AWS Lambda serverless functions in general, is that the slow startup time is perhaps the most would come up at the top of the search. So, but what basically what they did is they had a new product called essentially it's a snapshot of a running container, so that you can start all the services in the container and take a snapshot of it, and then start from next time you start from the snapshot. So that's definitely is in the right direction. That's because some people have said for a very long time that the cold start perhaps doesn't really matter that much because you can keep warm. But keep warm, waste a lot of resources and breaks the serverless or microservice pricing model, because you have to have those services running at all times, have CPU allocated to them. And I think one of the most compelling arguments that I've heard is that planning for the worst case scenario could be a huge waste of resources, because you never know when the worst case scenario is going to come. You never know when the container could take 10 seconds to start up, right? So you always have to prepare for that situation, and that results in certain things you can't do within your architecture. Right? So those are the things that I think are issues, right? That's of the current way of running microservices, running them inside, basically running them inside Linux containers. Of course, container itself may not be safe, but there are solutions for that. However, in order to implement those solutions, I think the typical ones, the gvisor, or there's solutions that to make containers more secure in a multi-tenancy environment. You would makes above two problems worse, because because you need extra layers of security added to it, right? So those are some of the issues. So that leads to the question, there's two ways to solve the problems that I have just mentioned. One is through software architecture. One of the ways is, which I believe is how they're going to do it in Twitter, is to go back to what we call mini monolithic applications, bundling, so you have multiple microservices and you bundle them together, right? That's essentially to create a in development, you have microservices, but in deployment, you still have those things chained together. So another way to do it, of course, is can we have a dramatically faster, orders of magnitude faster and a smaller application runtime for those microservices, so that we don't need to worry about those issues, right? So that we can keep everything at code and then just to start them as needed, just as the way that it's intended to be used, instead of having additional architecture patterns added to it. Right? So that leads to the whole reason why we want to use WebAssembly on the server. So WebAssembly on the server, if I may, to summarize it in one sentence, is opinionated runtime. So it's not like Linux container runtime, which runs anything that the Linux runs. WebAssembly has its own SDK, has its own requirements. So that's why we call it opinionated. It's a very opinionated way of doing things. Opinionated runtime, but it's optimized for lightweight services like microservices, right? So if you look at a WebAssembly image, a WebAssembly application with a comparable application that written in traditional languages and bundled in a Linux container, we do not do super optimization to remove all the Linux libraries from the container, but have those say have Alpine in it or have Ubuntu in it, right? That's you could typically result in 2 orders of magnitude in terms of size reduction. That's which we're going to show in a minute. And it's also when it comes to startup time, it's sub-milliseconds. I think even with Lambda, that's what they showed at keynote, to have the snapshot capability, it's still, we are talking about hundreds of milliseconds in startup time. They reduced that from seconds in order of 6 to 10 seconds to 200 to 600 milliseconds, right? But we are talking about sub-millisecond startup. So it's another 2 order of magnitude, 2 or 3 order of magnitude improvement from the current container-based solutions or VM-based solutions. And at runtime, it has near native performance, because compiler techniques we can apply to WebAssembly. So and because WebAssembly was born in a very adversarial, hostile environment, namely its browser, and then its first application on the server side is really the blockchain running smart contracts. So in both cases are what we call hacker magnets, right? That's people tends to hack those environments all the time. So it's designed from ground up to be secure. So it has a very small attack surface, and it has a very sensible security model, which what we call capability-based security, meaning that's by default it doesn't allow access to anything, and so every access, anything that you need to access need to be declared, right? So so it's completely portable across different platforms. In that way, it's very similar to Java. That's it's write once, run anywhere. Doesn't matter the underlying operating system or the CPU architecture, as long as WebAssembly runtime runs, you can use it, right? It's more or less programming language agnostic at the moment. It works best with compiled programming languages like Rust, C++. It works through a lot of effort in the community. It also works with things like JavaScript and Python. We're going to talk about that in a minute. So it plays well with container tools like Kubernetes, Docker, Podman, and Dapr as well, right? So those are the things that's through the past 2 years of development of WebAssembly on the server that brings allows WebAssembly to bring to the table, that provide potentially provide alternative to Linux containers in those in microservice type of applications. So of course there's I've said orders magnitude smaller, orders magnitude faster. So where are the trade-offs? It's that's because there's no free lunch, right? If you hear people say something so and so has unlimited benefits, there's no downsides, it's probably a scam, right? So definitely WebAssembly also has its own trade-offs. That's why we call it opinionated framework, right? So most importantly, it's not a general OS environment. So you can't just take your Linux application and expect to run inside a new container. So the Linux container is a general OS environment. So everything you run on your local machine, on your Linux machine, you can run it in the Linux container. But WebAssembly is not. It typically requires new SDKs to use new features. That's why we have as we'll see in a minute, we have a Dapr WASM SDK that's designed to access the Dapr services, right? That's it needs support for new programming languages. Specifically, it needs support for SDKs for for common computing tasks or common services that to be ported to WebAssembly. That's also the issue that Yaron has mentioned in his last talk, is that because WebAssembly lacks some of the common features that we find in the enterprise world, so using the Dapr services with its connection to databases, to messaging queues, to key value stores, to secret stores, would supplement and enhance WebAssembly's capability in that regard. So that is, I think it's a very nice, complementary points that for both WebAssembly and for Dapr, right? So so there's no free lunch. There's more work on the developer side to to get involved and then to develop applications that designed to be deployed in a WebAssembly environment. Okay, so a little bit about WASM Edge. So WASM Edge, is when we started the project in 2019, there's already a couple of WebAssembly projects out there, and why do people keep asking, why do you guys want to do a new one? I think we have a very specific goal of doing a WebAssembly runtime that's optimized for the server. So we have really no consideration for the browser. We have some consideration for running on devices, meaning running on IoT devices, running on Raspberry Pi, because the WebAssembly runtime can be stripped down to only 2 megabytes in size. So it can be embedded in a lot in small devices. However, that's not the primary use case that we are seeing today. What we are seeing is really the server-side use case, is to, for lack of a better word, to use WebAssembly like the JVM, right? So you have you use it from server applications in data centers, and to do that, you need to enhance WebAssembly capabilities in ways that goes beyond the standard. So I think that's the chief reason why we started this project. For instance, network connections. For instance, today a lot of services requires AI and ML capabilities. They need to access to the underlying GPU or the tensor frameworks, right? So those are things that's enhancement that we do at WebAssembly, and we also provide a very good support for JavaScript. With a lot of the Node.js APIs already supported today. So that which is another thing that confuses people is that you typically see in the browser is a JavaScript runs WebAssembly. The application is written in JavaScript, and then you have some part of the application written in Rust. They are compiled to WebAssembly and runs there, right? On the server side, we are using WebAssembly to run JavaScript because, as I said, we are using WebAssembly as a container format. It's the same way the Linux container runs Node.js. It's the same setup, right? So the WebAssembly runtime runs a JavaScript and Node.js runtime, and to support applications that are written in Node.js, right? So that's a quick summary of this project. And so one of the interesting things, which I think is also relevant, very relevant to Dapr integration, is that we are WebAssembly is now fully integrated into Docker desktop, the Docker engine, and the Docker desktop had a technical preview during KubeCon, and they're going to have a official release that embed WebAssembly in I think next week, or early December at least. So it's the PR has already been merged. You can see that, and but you can download the technical review already, and I would highly encourage you to try out this the example that I showed on this slide. I wouldn't because the limitation of time, because we want to focus on Dapr, I wouldn't go through that example, but I can talk about it verbally. That's so what it does, it's set up a typical 3-tier microservice applications or service applications, right, through Docker Compose. And so on the back end, there's a MySQL database running inside a Linux container that is managed by Docker Compose. And that database is about 120 megabytes big. On the front end is the Nginx web server. It's primarily just to serve the static web page, because most of the interaction is done through the JavaScript in the web page interact with the microservice on the back end, right? So it's the Nginx web server that mostly serves static web page and JavaScript. That one is about 20 megabytes. So you have 20 megabytes, 120 megabytes, and then the entire application logic is sitting in the middle. It's what we from the Docker point of view, it's another container. It's called a WebAssembly container. So it's a WebAssembly container sitting in the middle that it has all the logic where it's exposed HTTP interface to Nginx. So Nginx can be used as a proxy to send a request into the microservice. The microservices would pass the request from the HTTP request, generate the SQL statement, and maintain a connection pool into the database, and then execute the SQL statement in a database to store the data, right? So the application really is a very typical database access application. You can essentially, as we're also going to see an example like that in a minute, through Dapr though. So that's what's most important is that the container, the WebAssembly container in the middle is only 2 megabytes. Okay, so the whole application plus runtime is 2 megabytes. And the container on both ends, that doesn't contain any application logic, are tens of megabytes or hundreds of megabytes. And what Docker Compose does, the new version of Docker Compose does, is that it treats those 3 containers as equals, right? So that allows us to run Linux container and Wasm containers in the same tool or in the same setup, right? So that essentially running them side by side, which I think is a use case we want to see with Dapr integrations. So I'm going to talk about in a minute. So now I've just described a very typical, very traditional 3-tier database access applications, and I would really encourage you to try that out in a Docker desktop preview, or wait for a week until the next release of the Docker desktop come out, and you can try that. And you can inspect the Docker images and see those 3 containers running side by side. And what the architecture flexibility it gives us is because the application itself that sits in the middle becomes so small and start up so fast. You can keep 1 running, or you can keep 2 running. So on the front end, the Nginx could become the load balancer, right? So you could deploy hundreds of those, services that are in the middle, and you can keep them cold all the time. And then, whenever a request comes in, you spin one up. It's start up in milliseconds, and then once it's done, you shut it down, or you can do a lot of things with a truly microservice that only take 2 megabytes. That's in the middle, right? So that's that's why I like Docker, our partnership with Docker, is because it's really visualize this whole setup. Because in the past I would have to have a long lengthy tutorial to show how to set up Kubernetes with CRUN and Podman, right? That's to have those container, the Wasm containers and Linux containers running side by side. But with Docker Compose, it's just 1 command, just the Docker Compose up, if you have time, I really encourage you to try that. So that's enough for WebAssembly itself and and Wasm Edge. And now we want to focus on more of that's the integration with the Dapr SDK. So as you can see, there's we have done a lot of work in WebAssembly itself, so that it supports networking, asynchronous networking, in particular Tokyo in Rust side, and then MySQL async on the database side. And so so there's so it lays the foundation to say from the WebAssembly application, I can now already talk to the database and talk to the Nginx web server. And can I talk to the Dapr sidecar using WebAssembly SDK for Dapr? That's is a problem that we want to solve with the Dapr Wasm SDK. So here's the I think a simple architecture for that setup. Currently, we only implemented HTTP, but I think gRPC shouldn't be, there's in principle, there's nothing that blocks, supporting the gRPC interface. It's just a matter of manpower. That's also why I'm presenting here, is to generate more interest from you guys to see, to see if there's, to see if there's interest to contribute to this project, right? So essentially, you can see on this graph, the Dapr sidecar is at the top. And then the microservice written in Rust is in that pink box. That is the WebAssembly runtime. So the WebAssembly runtime, inside this WebAssembly runtime, this Rust application starts its own HTTP server written in Tokyo, right? It has its own business logic. And then through the Dapr SDK, and what we call Dapr SDK for WASI, it communicates with the Dapr sidecar through the HTTP service interface, right? So that allows the business application inside WebAssembly to consume all kinds of services that the Dapr sidecar could provide, like service discovery, service invocation, and the resilience service that's that's just been mentioned, and the key value messaging queue and all that things. That's through a unified API that's that Dapr provides, right? I think that's so I think that's at least that to me that's a very compelling way of using incorporating Dapr services into a lightweight runtime. So the runtime still stays very lightweight. The microservice itself still stays like extremely light, but it communicates with the service provider outside of it, right? So that's the architecture, so to speak, right? So I want to show you an example. The example is here. That's it's a second state / Dapr -wasm. It runs 3 microservices, each with attached Dapr sidecar, right? So there's and then there's a web interface. So I think perhaps I should do a demo first. Let me do the demo first, so that let me change my screen share to the demo, so that I can. Sorry, let me get. There we go. Okay, let me. So this is what it looks like after it's deployed, and the front end we don't have. It's the front end is completely static HTML and JavaScript. Okay, so the way it's set up is what we call Jamstack, right? Is that you have a complete static front end that can be deployed by, say, GitHub Pages, or on CDN, Overcell, or Netlify, places like that. And then all the services are provided by microservices on the backend, right? So it calls microservice, and what it does is that the microservice, the service exposed on the backend is through the Dapr sidecar. So this JavaScript API contacts the Dapr sidecar to ask for which backend services you want, and then consume that service, right? So what you see here is a web interface to say you can upload a picture and do something to it, right? So let's upload a picture like this. And then I say which API I want to use. So there are 2 microservices on the backend that provide service to this front end. One is a grayscale, and another one is classify. So let's see what grayscale does. What it does is that, by the way, the service on the backend is all code, and I'm in a hotel Wi-Fi connection, so it's slow, right? But you can see it's reasonably fast. It comes back reasonably fast, right? So this grayscale is that I take the image and send the image to a microservice behind a Dapr sidecar. And then that microservice processes it and send back in the HTTP response, send back a grayscale image. So you can see that that's the color become black and white, right? So that's good. That's so from the completely static front end, I can select one microservice on the back end. I can switch to another microservice to the backend. Maybe I don't want to turn that into grayscale. I don't know what the image is about to begin with, so I want to know what's on that image to begin with. Right? So what this does is that this sends routes the image to another microservice. It's through the Dapr service invocation API, and that microservice has access to the TensorFlow API in WebAssembly, right? So in WASM Edge, because a lot of our use cases are Edge AI use cases, so we can have TensorFlow, PyTorch, or OpenWino in it. Right? So it sends that to the microservice, and the microservice calls TensorFlow and applies the MobileNet model to it, and then gets a result and look up the result table to find an English name for it. And it says it thinks the picture is a rock crab, which I think is really close, right? That's with a high confidence. It's I didn't bother to convert that into percentage, but you can see this is this is an integer, right? That's the highest value is 255, and now it shows a high value. That's so the system is fairly confident that that's it has recognized what's on the classified what's on the picture, right? So this web page is completely static, and on the back end, I've shown you on the back end there's 2 services. So let me go back to the architecture diagram of this system. Okay, so the static web page is here. As you can see, that's it's just HTML and JavaScript. It can be hosted anywhere. It can be even hosted on the, say, distributed file network, whatever, or even locally on your own computer. That's fine. Just open the HTML. That's it's gonna have JavaScript in it, right? So JavaScript, it uses JavaScript HTTP request, API calls to any of the Dapr sidecars that are on the backend. So on the Dapr sidecar, use the service invocation API to find out which service it wants to invoke, right? So on the back, so all those green services are written in WebAssembly and deployed in what we call WebAssembly container. And those Dapr services are deployed in today they're deployed in a Linux container that runs Dapr, right? So it uses a service invocation API to find out whether it needs to do grayscale or need to do classify, and then sends the data to the corresponding Dapr sidecar, and that sidecar is responsible for invoking the service, right? So that's the service discovery and invocation part. But in here, you can also do state management, as we'll see in a minute. In the code that we save some log data, observability data into the Dapr sidecar, so that we know how many times the service is being called, who called that, and things like that. And then on the other side of the thing, so those are service invocation, and then on the other side, it's a logging service. So when the request from clients come in, it also tries to save into a database, to save a log into the database, into a MySQL database on the backend. So here we have an event service that is also written in WebAssembly. So the Dapr sidecar would be able to route that to all the requests into the event service and then save it to MySQL. So what happens is that you have a static web page that's have a request come in, and then have the Dapr sidecar to handle all the communication for you. And so it knows in this particular request, you need to do grayscale and events. So it calls those two services, right? And in some other events, it may need to do classify and events. One of the very practical benefits of the Dapr service in this particular use case is that it does call CORS for free, right? So because one of the thing about Jamstack service is that you want to use the static web pages hosted in one place to call microservices in another domain, and typically it's a security risk that the browser doesn't allow you to do that. You have to make some configuration on the back end to make sure that the microservice accept this kind of requests, right? So that's the Dapr sidecar itself, the HTTP service interface provided by the Dapr sidecar can be configured to do that. That just saves another Linux container that has to sit in front to to do the cross management, right? So I really find a lot of the services that provided sidecar valuable. That's just a very small example. So that's a architecture diagram of this whole thing. That's you can see it's a very similar, which is very similar to a typical or traditional Dapr application, except all the services are now running WebAssembly instead of running Linux containers. So let's spend a couple minutes to look at the code. The purpose is really not to show you how the code works, but to show you it's fairly simple, and all those can be written in JavaScript as well. By the way, I'm just using Rust because I'm more familiar with it, right? So this is a code for the image classify. So the image class on the left side is a main function. The main function, as you can see, is very straightforward, right? It's just using the Rust Tokyo framework, which is a non-blocking high-performance socket framework, a networking framework. So it opens up a network connection at the application port, right? And then it says for every request that comes in, I want to pass the request to a function called classify, which the classify function does almost all the work, right? So and then just start the server and wait for request. That's the whole main function. And then inside the classify function, we start the Dapr client, right? Because in that Dapr client, we need to do the event service, because now we know the service is routed to the image classification service. And now we, actually here we invoke Dapr to do two things. One is to find the event service and log it, save that event to the database. That's the image classification has been called, because the image classification microservice has received this request, right? And then it also saves some data into its own state store. Why do you need to save something in a relational database and also save something local to the microservice? Is because you can have temporary data that's required for the microservice, right? That's, for instance, for rate limiting features. That's maybe you only want this IP address, each IP address to have 10 invocations for every 10 seconds, something like that. And so you can save all those temporary data at the state store in the local to the Dapr instance that runs this microservice, right? And then save the global data into the database. I don't know. I think I still have a couple minutes, so actually let me show you the code for the classify function itself. Okay, let me. So here we go. You can see this is, as we call the classify function. Actually, I'll show you here. So this is a function I've just shown you. This is the main function that starts the server. And whenever a request comes in, it calls the classify function, right? So here is the actual classify function. The classify function takes the HTTP request and generates a HTTP response. It's that simple, right? In this particular case, it's classified. So it takes the HTTP request that contains an image, and the response is a string that basically tells you what's in the image. And what it does is that it loads the TensorFlow model and the TensorFlow label file, because after you process the image, you generate a number. The number corresponds to an English label. In our demo, it's a crab, right? In that label file. That's so you need those files. You have them in your application, and then depending on what type of request will come in, you can generate different responses, right? So if you just post, have a GET request that's the root of the service, it's gonna say that's it's not supported here. You have to submit an image, something like that. But if you do a post request to the classify URL, that's what you it's really very simple. It's that it's takes the image out of it, and then it's passed the IP address and save it in the Dapr state store, which is the rate limiting feature we just talked about. And then it takes the image out of the request and generate a flat image. It's that's required by the TensorFlow model. Then it just says run TensorFlow, which is just really one single one command, and it gets the result. The result is an array of numbers. It's that shows you the probability for each of the known objects, right? So it's have like 1,000 objects that the model is pre-trained, including crab, cars, and everything. And so it's gonna return that array. And with each index, you're going to have a corresponding probability. And then the rest of the code really is to figure out which index has the highest probability, and then look up the index file to find the English name for it, and then generate the response and then send it out, right? So so the reason I want to show you is that people used to say doing machine learning or AI inference on Python is easy, but with support for WebAssembly SDKs and things like that, it literally takes a couple lines of code to do that in Rust, and also to do that in Node.js as well, in JavaScript as well, right? So then here is more Dapr demonstration, to connect to to create events and send to the event service to be saved to the database, right? So this really is the whole application. It's it's like two screens, and it's it does something that many people might consider quite magical. Is that I send you a picture and you tell me what's on the picture, right? That's that's one microservice, and I want to show you another one, which sorry.
And just a heads up, we have about 5 minutes left, and maybe
Yes.
1 or 2 minutes for questions, because I'm sure there are some.
Got it. Yes. So I'll finish in a couple minutes. Okay, sorry. All right. Okay. So this is what you have seen. And then this is the event service. The event service is slightly more complex because you need a connection port to the MySQL database. So this is the main function. So not only it needs to start, so if you can see my cursor, that's this part, the part to start a web server is the same as before. But all the code that in front of it is to start a MySQL connection port. And then, connect to the MySQL database, right? So, and here you can see, there's when the request comes in an HTTP post, it has data in it. It's what it does is that parse out all the data. The data comes in a JSON format, and it's parse out all the data, and then create a SQL statement to save this data into the MySQL database, right? So it's a very typical, I say, database access service, right? So you have data coming from front end, and you parse it, and you generate some SQL statement to save into the database. So that's the event service. And so we have shown the demo. Yeah, so that's really is the last slide. That's so there's we have shown a very simple application that's it's a multi-container, but still fairly simple application that is written in Rust using the Dapr Rust SDK, the Dapr WASM SDK, and deployed with Dapr, right? So it used Docker Compose to set up those multi-container environment and make them work all together. And so we really want to see this type of deployments and this type of architecture being simplified and being have more tutorial and other environments like Podman and Kubernetes. We know it can be done. Just needs to it needs to be demonstrated, and we need to write up the documentation and things like that. And another thing is that the Dapr SDK for WASM, at this time we have some capabilities. As we can see, we have state store, secret store, service invocation, things like that. We really would like to have the complete Dapr SDK supported in WebAssembly, so that meaning to expand this SDK and implement all the features, which is something that's our to-do list, and that's also something we would hope the community would be able to participate, right? So that's additionally, we not only wanted to in Rust, we also wanted it in JavaScript as well. So maybe the JavaScript part could be easier because there's easier HTTP APIs to use in the JavaScript world. And maybe like Yaron has said last time, now we have mixed container applications, with WebAssembly running the services and Dapr running the sidecar in Linux containers. Could we put at least some of the functionalities of Dapr into web services as well? So we have the sidecar running web services as well, right? So that's maybe something that's we can brainstorm, or that's something if anyone in the community want to try it, we'd love to see that as well. So yeah, that'd be my end of my talk. Sorry, I ran a little long, but that's so hopefully. Yeah.
This is great. Thank you. A really impressive demo as well. Yeah, we have like 1 or 2 minutes left. I want to make sure if there are any questions, feel free to, I think everyone can unmute at this point and just feel free to ask a question. I don't know, Artur, you might have had a question, I think I saw at one point.
So the question was, Michael, first of all, this is great, and thank you for showing all of that. The WASM SDK you wrote, does it use the Dapr Rust SDK, or do you just use straight out HTTP and gRPC primitives?
And at this moment, it's just HTTP, because the Rust, the Dapr Rust SDK still has some other dependencies that we can't compile to WebAssembly. So that part is it's parallel work that we are still trying to see. Because I think its dependency on tonic is one of the issues. That's but but at this moment we just had a HTTP interface.
Yeah, no, that's perfectly fine. Yeah, no, thank you for that. We don't have much time for my other questions, but I really would like to see how we can invest in this more. Actually, someone from the Dapr community pinged me last night, showing me a POC they wrote about invoking Dapr actors written in WASM, which is really interesting because they talked about like being able to invoke 50 million WASM actors per one Dapr instance, and so that was quite amazing. So I'm going to take a look at that. But yeah, you know, we're in touch, and I'll reach offline to you. We have a WebAssembly Discord channel for Dapr and WebAssembly talk, so we can talk more there, and we can continue the discussions there. But again, I think it's great. And Michael, please, for the next presentations, I always see you demo the Rust crab. Please try it with a gopher next time if you can.
Okay, I'll train a model for that. I'll train the model to recognize all the mascot in cloud native space. So,
Okay, cool.
thanks.
All right. Well, thank you again, Michael, for that presentation. And yeah, that wraps up the 73rd community call. Thanks everyone for attending. We'll see you in the next one.
Thank you. Yeah.
Bye.